Live. Hello again. I thought I'd make it a bit more formal this time, now that I know what I'm up to. I appear to have no screen. Okay, that one's not there. Let's just see if we can capture the screen. There we go, that's better. Let's have a look. No watches so far. I'll just pop in the first question. And the first question is an IB question, actually, a multiple choice question from the IB standard level around uncertainties. Ooh, that's quite a bit bigger than we needed, isn't it? Let's just shrink it down. Pop it back in there. Nope, still all too big. See if we can get it in the right place. There we go. It says the radius of a sphere is measured with an uncertainty of 2%. What's the uncertainty in the volume of the sphere? Now, I've got a few people coming into the stream now, so if anybody wants to have a go, maybe you've watched a video I posted a second ago about combining uncertainties. Maybe not. Either way, see if you can have a go and pop the answer in the chat. So maybe if we start thinking that the radius of a sphere is measured with uncertainty of 2%, what's the uncertainty in the volume of the sphere? So we know that the volume of the sphere is 4/3 pi r cubed. Yep. So there's no uncertainty in these two, so we're not worried about that. Our only uncertainty comes in r, and what we've got is r times r times r. I wonder if anybody who's watched the uncertainties video already can have a go at answering that one. If not, I'll just stay talking to myself, which is fine. I love talking to myself. So, if you haven't watched the video, then what we're going to be able to find is our percentage uncertainty in V is going to be our percentage uncertainty in R. We're going to add this 3 times. So what we can say is if we've got a power, so for something raised to the power, and we're adding the percentage uncertainties, we multiply the percentage uncertainties by the power. Colour in there was 0.67%. Okay, so remember, if we're adding the uncertainty in R 3 times. We've got a percentage uncertainty of 2% in R. So what you've got there is 2/3. So if we do that, we've got 3 lots of the percentage uncertainty in R, which is 3 lots of 2%. Should be a bit bigger than 0.67%. I wonder, can I see who's watching? See how many people are watching. Fancy we another go at that one, Callum? Correctamundo. There you go, 6%. 6% is our uncertainty in V. And don't forget, good job, don't forget, if we were to want to express our uncertainty in V, then what we'd actually want is V plus or minus the absolute uncertainty in V, and then some units afterwards. Yep. So we don't want to have a final answer with a percentage uncertainty in it. Right, let's see if we can find another one for us to have a go at. Use a mouse for this. I have to make it nice and small. So this one's going to be a bit more tricky. I want to put it in there. There's the next one. There's the next one. So this time we've got a volume of a cylinder. So our cylinder looks like this, with radius R and height H. So it gives us that the volume of the cylinder, or the percentage uncertainty in the volume, equals 10%. It gives us that the percentage uncertainty in H is 6%. And it gives us our equation, which is V is pi r squared multiplied by the height. So if I was trying to find the percentage uncertainty in V, I'd want to do, so I've got r raised to the power of 2, so I've got 2 lots of percentage uncertainty in R. So I'm combining uncertainties, I'm multiplying things together. So if I'm multiplying things, I'm adding the percentage uncertainties, remember. So then I want to add on the percentage uncertainty in H. So I think I need to figure out something for me to do while people are having a think. And by people, the only people I know that are in the stream is Callum. Well, there are 2 other people hiding. If you're hiding and watching, do say hello. Callum Osborne with a 2% is spot on. Look at that. So we know in this case that we've got an uncertainty of 10% here, which is 2 lots of the percentage uncertainty in R, plus 6% in H, which gives us, if I can rearrange this and move this 6%, I could do it the long-hand way, minus 6% of each side, which gives me 4% on that side, is 2 lots of percentage uncertainty in R. So percentage uncertainty in R is 4% over 2 equals 2%. That's spot on. Very good. Very good indeed. Okay, let's do something a little bit more tricky, shall we? So if you're watching along after the fact, feel free to pause the video whilst you have a go at the questions, and then we'll go through them afterwards. So the next question says, which of the following, that's not what I wanted, copy that one. It says, which of the following is a possible unit for impulse? Which of the following is a possible unit for impulse? I've got Newton seconds to the minus 1, kgms to the minus 1, kgms to the minus 2, or second newtons to the minus 1. So what do I know? What do I know about impulse? I know that impulse is force times time, and I know also that impulse is change in momentum, or mv, so our final momentum minus our initial momentum. So we know a few things about this. We know that our force is newtons. Callum's gone with A. Keep thinking. We know that our time is in seconds. So immediately we haven't got newtons divided by seconds, which is a pain. We've got newtons times seconds, which is good. We haven't got that one. So we've said it's not A because it's actually newtons times seconds, and it's not D because it's not seconds over newtons. Okay? We've got change in momentum, which is mv minus mu. So for mv, or momentum, we've got kilograms multiplied by meters per second. Okay, so kilograms multiplied by meters per second. So B is our correct answer. So if we're taking things away, that's right, got it on the second time, great. So if we're taking things away, then we keep the same units. kgms to the minus 2, if we think about force just for a second, if F equals ma, then if we look at the dimensions of m and a, then that's kilograms multiplied by ms to the minus 2. So this one here is impulse or momentum. And then for future reference, kgms to the minus 2 is force. Excellent. Let's do a couple more, shall we? Now we're getting to the realm of the ones that I've just literally copied and pasted and not done already. So let's pop this one in here and get that other one in as well. So it's a railway truck of mass 8,000 kilograms, travels along a track, velocity 2.5 meters per second, collides with a stationary truck of mass 12,000 kilograms. Two trucks move together at the same velocity after the collision. What's the change in momentum of the 8,000 kilogram truck due to the impact? Okay, so we can think of our initial conditions. initial conditions, so we've got, think about conservation of momentum. We've got mu or m1u1 plus m2u2 equals, in this case, it's going to be m1, because they stick together, plus m2 times v. Okay? And they move together at the same velocity after the collision, right? So the first thing we're going to have to do is take a look at this value here. So my second truck is stationary, so that one is 0. So my first truck is 8,000 times 2.5, and in order to find v, we're going to divide that by m1 plus m2. If my maths in my head is working, that's 20,000 kilograms. Just pause there for a second while people have a go. So if we find our final velocity, then we'll be able to find the final velocity of the first truck. So initially, if I take this top part, this is our initial our initial momentum, which is 20,000 Newton seconds. So when we divide 20,000 by 20,000, we get 1 meter per second. Okay? So that is our initial velocity of our 8,000 kilogram truck. For our final velocity of my 8,000 kilogram truck, I want to do my initial mass multiplied by the final velocity. So that's 8,000 kilograms times by 1, which is 8,000 Newton seconds. So now we've got our final momentum, and our initial momentum is in there. So our change in momentum, actually you'd expect this to be negative, but I don't think it's going to give us, there are no negative options. Let's get rid of that. So my change in momentum would usually be my final momentum minus my initial momentum. So if I take 8,000 to be my final momentum, and then take away 20,000, because my change in velocity, my change in momentum, it goes from having more momentum to having less. My change is going to be minus 12,000 Newton seconds. So the answer is B. We've got no one in the stream answering the questions, which is a shame. 3 people watching, no one having a go. We'll do one more, and then I think I'll probably make it time to go to bed, because I've got to teach. Oh, I'm going to cut out part of my logo now, aren't I? Hang on. Because I've got to teach you guys tomorrow. Go back. Right, let's take a look in here. So no calculations with this one, potentially. Pop that one back up. Get my pen back. So this one says, a gas molecule of mass m moving at velocity u collides at right angles with the side of a container and rebounds elastically. Which one of the following statements containing the motion of the molecule is incorrect? So the first thing we always want to do is draw a diagram. So if that's my wall, that's an arrow. Gas molecule, mass m. So we can do a few things. It's going to have velocity v. Let's change that. It's going to have velocity u in that direction. So this is before. In our after scenario, we've still got our wall. We've still got our particle, mass m. But this time it's going in this direction. Put the arrow back on there. This time it's going in this direction, but my new velocity is minus u. Now I know it's minus u because it rebounds elastically. So there's no energy lost. Okay, so I come in at a certain velocity, I leave at a certain velocity. Energy's conserved in elastic collision, and momentum's conserved in an elastic collision. So what we can calculate is, if I try and find, it usually in these situations where we have a collision of a wall, we're trying to find the change in momentum. So before we even look at the answers, we know the change in momentum is our final momentum, which is minus mu, minus our initial momentum, which is u. So our change in momentum is minus 2 mu. Okay, so we know that that's a thing. It says, which of these following statements concerning the motion of the molecule is incorrect? So we look down the list and it says the magnitude of the change in momentum of the molecule is 0. Alright, so that one's looking a bit suspect already, given what we've calculated. The second one says the magnitude and the change in momentum of the molecule is 2 mu. So we just calculated that. That is correct. We talked about elastic collisions before. Let's look down at D. It says the change in kinetic energy of the molecule is 0. So we said in elastic collisions, kinetic energy is conserved. Energy is always conserved, but in elastic collisions, kinetic energy specifically is conserved. So there's no change in kinetic energy. So that's right. So we've got two left, A and C. So look at C. The force exerted by the molecule on the side of the container is equal to the force exerted by the container on the molecule. So that sounds a lot to me like an interaction pair. Okay, so the force exerted on A by B is equal to the force exerted on B by A. Okay, so that is Newton's third law in practice. So that's correct. So for the answer to this one, we're looking at A. Fantastic. That's going to be the last one for tonight. It is 10 to 12. I've got to come and teach you lovely people tomorrow. So, good night. Thanks for watching. I hope you found something useful. And I'll see you another day.